Okay, class, so this is section 3.6, Polynomials and Rational Inequalities. And this slide here just talks about the definition of a polynomial equation, which it is any inequality that can be put into one of the forms. One of the forms is f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than 0, where f is a polynomial function. Now, just as in section 3.5, there were steps to graphing rational equations, well, for 3.6, there's a procedure for solving polynomial inequalities. And it consists of 5 steps, with the first one being express the inequality in the form f of x is less than 0 or f of x is greater than 0. Then you solve the equation f of x equal to 0, whereas the real solutions are the boundary points. Then you draw a number line and locate the boundary points on the number line, dividing it into intervals. So you write it in interval notation after you find it on the line. Step 4 is where you then create a table. And in that table, you're choosing one representative number, called a test value, within each of the intervals that you found in step number 3, and you're evaluating f at each number that you select. In step 5, you write a solution set, selecting an interval or intervals that satisfy the given inequality. Now, this next slide just says that, hey, this procedure is not only valid for greater than or less than, but it's also valid for greater than or equal to, as well as less than or equal to. But we also must pay close attention to our boundary points, because we know if it's greater than or less than, we're just using parentheses, whereas if it's greater than or equal to or less than or equal to, we're using the brackets. We're using the brackets like this. If it's greater than or equal to or less than or equal to. Whereas if it's greater than or less than, we use parentheses, okay? All right, so let's put this to test. Let's use a problem. So if we have the problem x squared minus 7x is greater than negative 6. Step 1 says express the inequality in the form of f of x is less than 0 or f of x is greater than 0. So for this problem here, we see they're using the greater than sign. So we will be using this right here, f of x is greater than 0. But first we have to write it in that form. So it's x squared minus 7x plus 6 is greater than 0. We had to bring the 6 on the other side. We had to bring the 6 over here in order to make it like this here. Once we did that, that made the 6 positive, and now we have satisfied the conditions of step number 1. So let's go to step number 2. Step number 2 says solve the equation f of x equals 0. The real solution are the boundary points. So we have x squared minus 7x plus 6 greater than or equal to 0. So we're solving this. So to solve this, we know we have to set something equal to 0 or factor it. So we know we can't just set it equal to 0, but we can factor this here. If we factor this, we're going to have x minus 6, x minus 1, equals 0. Once we do that, then we set each of these equal to 0. X minus 6 equals 0. X minus 1 equals 0. From there, we have x is equal to 6 and x is equal to 1. So, the x-intercepts of f are 6 and 1. So we'll use these x-intercepts as boundary points on the number line, which is the next step. So here we go for our number line. So let's draw our number line. So my notes up here tells me that my boundary points which we found on the last problem are x equals 6 and x equals 1. So I'm just going to draw this line here, put a 0 there, negative 1, 1, 2, 3, 4, 5, 6. I'm just going to put a 7 here as well then. Okay, so I know what my boundary points are. It is boundary points for 1 and 6. Alright, so now what I have to do is divide the number line into 3 intervals. So once I do that, it's done like this. It says 2 intervals up here because just speaking in a very generic term, but really it's 3 intervals because we have this interval here. Oh, I'm not drawing that right. Let me erase this. We have this interval here. We have the interval here. Then we have the interval here. So approaching from this direction, this interval is negative infinity to 1. The union of 1 to 6. The union, and our last interval is 6 to infinity. Okay, so negative infinity to 1. You make this a little bit better. It's negative infinity right there. This is negative infinity to 1, 1 to 6, and then 6 to infinity. So these are our intervals right here. So let's go to the next one. I'm going to write my intervals again. Negative infinity to 1, infinity to 1, union 1 to 6, union 6 to infinity. Okay. So now I have to choose one representative number called a test value within each interval. So I'm going to draw a table here, my interval. Call this my interval, my test value. What I'm substituting it for, and my conclusion. Draw my table here. So I have my interval negative infinity to 1, right? Negative infinity to 1. My test value has to be between negative infinity and 1. So that is, we could pick any number. I'm going to select 0. Why make it more difficult for myself? So then if I substitute 0, well, I'm going to make one more small change here. 1 is 6, 6 to infinity. So I'm going to put my interval notation right in my table. I am going to remove this here and replace this with the original formula, which was the x squared minus 7 plus 6 equals 0. x squared minus 7x plus 6. So 0 is my test value. And if I plug 0 up here, so this would be 0 squared minus 7 times 0 plus 6. What would that be? That would be 6, right? Exactly. So now a test value between 1 and 6. I'm going to say that will be 2. So then if I do that, then that will be 2 squared minus 7 times 2 plus 6. And what is that? Minus 4. I'm going to make this 6 look a bit better. Then if 6 to infinity, my test value is 7. So now I have 7 squared minus 7 times 7 plus 6. That would be 6. So my conclusion here is that my f of x is greater than 0. So f of x greater than 0. Here, my f of x is less than 0. F of x is less than 0. And here, my f of x is greater than 0. So, now that we have that there, we can then go into step number 5. And if you're saying, hey, how is your f of x greater than 0? Well, once I plug 0, if we just look at this one right here, once I plug 0 into this problem here, what it came out to be, and I'm going to do a lot of scribbling here, 0 squared minus 7 times 0 plus 6 equals 6. And 6 is greater than 0. So that's why f of x equals 0. Now, when I plug 2 in, the end result was a negative 4. Negative 4 is less than 0. So that's why that's less than 0. And so on. When I did 7 here, the end result was 6. When I plugged 7 into this equation up here, the end result was 6. And 6 is greater than 0, so f of x is greater than 0. Now I come over here to my last step. I write the solution set, selecting an interval or intervals that satisfy the given inequality. Well, if you remember, we said that if the value of f is positive, then f of x is greater than 0 for all numbers on the interval. And then we go back to the original problem. We saw that f of x was greater than 0, which the original problem was, after we solved for f of x, the problem was f of x, what was x squared minus 7x plus 6 greater than 0. So since we had that greater than 0, that's what we're looking for. Solutions that are greater than 0 here. Once we find that, which we found on this slide here, and it was this one and this one, we just come over here and we say negative infinity to 1 in the union of 6 to infinity. 6 to infinity. And that's the answer for that problem there. So I think that, as with all these problems, it's going to take practice. Like I said, the steps, do not be intimidated by the number of steps, because the steps are very clear in that they tell you exactly what you need to do. All you have to go in to do is just practice and do it on your own. Okay, that's it for this lecture. Thank you. Okay, let's do one more. 2x. Let me step back. 2x over x plus 1 greater than or equal to 1. So the first step here would be to bring the 1 over here on this side. That's the first step. So we would say 2x over x plus 1 minus 1 greater than or equal to 0. But now that we've done that, we have to find the least common denominator, which in this case is x plus 1. So once we find the least common denominator, we've done this before, we would say, well, not right there, but we would say, trying to figure out how I can have more real estate here, let's say 2x over x plus 1 minus 1, x plus 1, x plus 1 greater than or equal to 0. Alright, now we have to do some simplifying here. So then we have 2x over x plus 1 minus x minus 1 all over x plus 1 greater than or equal to 0. Then we simplify that. Once we simplify that, then what we will have will be, one second, go to the next slide. Then we will have, this is number 1 continued. We would have, I'm just going to write this over 2x minus 1 all over x plus 1. And that will be equal to x minus 1, x plus 1 greater than or equal to 0. Okay, so now that we have that, step number 2 is that we will set our numerator and the denominator of f equal to 0. So setting the numerator and the denominator equal to 0. And the real solution of those will be our boundary points. So, x minus 1 equals 0, x plus 1 equals 0. So our boundary points are 1 and negative 1. So now we go to step 3 and we graph those boundary points. Step 3, have our number line, 0, negative 1, negative 2, 1, 2. We find those on our number line. It's right there. Other one's right there. Then we divide the number line into 3 intervals here. So that would be negative infinity, negative 1, negative 1 to 1, the union of 1 and infinity. So now we have that done. Step number 4, we're choosing a test value in each one of these intervals here. So step 4, choosing our test values. So you draw a table. We know we have negative infinity to negative 1. We have 1, negative 1 to 1. And we have 1 to infinity. So then our test value goes here. We'll substitute it into there. And then we have our conclusion. So our test value between negative infinity and negative 1, let's say test value of negative 2. Test value between negative 1 and 1, make it real simple, 0, and 1 and infinity, let's just say 2 again. So, now that we have that, if we substitute a negative 2 in to the equation that we had, so it would be a minus 2, minus 1, all over minus 2, plus 1. What would that give us? That will give us a 3, right? Because it will come out to a minus 3, minus 1, positive and positive, just be a 3. Erase this here because it really doesn't go in this column here. Just be a 3. So I'm going to erase this line right here to make this a bit more wider. Equals 3. So we can say f of x is greater than 0. When a 0 is plugged in, that will be 0 minus 1 0 plus 1, that will be a negative 1 over a positive 1, which is a negative 1. So f of x is less than 0 here. Then 2 minus 1, 2 plus 1, and that will give us what? A 1 over 3. So this is f of x is greater than 0. Okay, so we have f of x is greater than 0 twice, f of x is less than 0 once, and we know from the original problem was x minus 1, x plus 1 greater than or equal to 0. So with that in mind, we're looking at this interval here, because greater than or equal to 0, and this one here. So with that in mind, we come over here to step 5. And for step 5, we write the solution set, selecting the interval or intervals that satisfy the given inequality. And that given inequality, once again, was f of x is x minus 1, x plus 1, greater than or equal to 0. So, based on our work in step 4, we saw that f of x is greater than or equal to 0 for negative infinity to negative 1, union 1 to infinity. That's what we saw based on step 4. However, because the inequality involves greater than or equal to, we must also include the solution of f of x equal to 0. In particular, the value we obtained when we set the numerator of f equal to 0. So if you recall, the numerator of f, which is this x minus 1, that's the numerator. When we set that equal to 0, x was a positive 1, right? So we must include the positive 1 in the solution set. So then the solution set will be negative infinity to negative 1, union, bracket 1, comma, infinity. You see, when it was parenthesis 1, we were not including the 1 in the solution set. We were including everything greater than 1, such as 2, 3, 4, 5, and so on. But when we put the bracket here, this is saying, okay, we are including 1 in the solution set now. So it's 1, 2, 3, 4, 5, 6, and so on. And the way we arrived at that once again is that because x minus 1, this right here, when we set that equal to 0, what is x? It's a positive 1. So you're only going to do that when you have this greater than or equal to. You look at that numerator, see what it is, set it equal to 0, and since that is 1, that's why we came over here and we changed this to a bracket instead of a parenthesis. We did not mess with the negative 1 because we're not talking about the denominator. When the denominator is set equal to 0, that's when we use the negative 1. Well, that's when we know x plus 1 equals 0, x is negative 1. But we're not looking at that. We only look at the numerator here, x minus 1, positive 1, and that's how we arrive at this solution right here. So, if you have a problem like this, and you just leave it in this state right here, it's going to be marked wrong. Once you get here, and you have a greater than or equal to, less than or equal to, you go and you look at that numerator, set it equal to 0, and whatever that number is, you come down here and you find a bracket that corresponds to that, and you change that parentheses to a bracket. Okay, and that is the conclusion of section 3.6, Polynomial and Rational Inequalities.